Happy Sunday, ladies and gents. I'm Derek, and this is probably going to be my last presentation or video in a while, so I hope it can be a goodie. Today I want to talk to you about the theory of acids and bases. Now, the presentation is comprised of two parts. The first portion is about the development of our understanding of acids and bases. And this part of the presentation really comes from a paper written by William B. Jensen at the University of Wisconsin. And so if you're interested in this development, and also as we talk about later, if you're interested in the generalized electronic theory of Lewis acids and bases, I highly recommend that you refer to his paper, which I cite as my primary source at the end of my presentation. Now, the second portion is an analytical example of an acid-base reaction that uses equilibrium constants. So I hope you can enjoy either, if not both, sections of my presentation. So first, what really motivated our study of acids and bases are actually two series of observations. The first key observation is that there seem to be two categories of substances, such that within the same category, substances behave in a very similar way. Say they all turn a particular indicator to a specific color. Well, across the categories, we have two substances across the two categories. They behave in a very different, very disparate way. And the interesting thing is when you add the two substances across categories together, that distinct behavior disappears. And that's what we call neutralization. And so, as we talk about later, all the definitions, the Arrhenius definition, the Bronsted-Lowry definition, and the Lewis definition, what they really are theories. They're considered theories in that they are our own artificial or scientific definitions that we try to use them to encapsulate these two natural observations. So in other words, there is a natural observation, there's a natural definition for acids and bases, and we're trying to encapsulate that by our own definition. So one first early milestone in our understanding of acids and bases come from the Swedish scientist Svante Arrhenius. You may recall Arrhenius from kinetics, right? The collision model, his Arrhenius equation. So what the Arrhenius definition of acids and bases really is that an Arrhenius acid is a substance that when added to water increases the concentration of hydrogen ions. And a base is that which increases the hydroxide concentration. And so an example of an Arrhenius acid may be hydrochloric acid, right? So when you add hydrochloric acid to water, you form hydrogen ion, which is really hydronium ion. So you kind of increase the hydronium ion, and therefore it's an acid. And an Arrhenius base may be sodium hydroxide, because when you add sodium hydroxide to water, it dissociates into sodium ions and hydroxide ions, and so you pump up the hydroxide ion concentration. Now recall that what we are trying to do here by defining acids and bases is we're trying to come up with a definition that can encapsulate as general as possible to two general observations. And so it turns out that the Arrhenius definition is not generalized enough, right? It kind of focuses on water as the specific solvent. And so there's a generalized definition later developed by the American chemist Albert Frederick Audemars German, who developed this solvent system model. And it has two premises. The first premise is that there has to be a solvent molecule that can ionize into a cation and an anion. As we talked about earlier, water is definitely one of the possible solvents. And another solvent may be ammonia, right? So when you have two ammonia molecules, two gaseous ammonia molecules, they may dissociate into an ammonium and also an azenide ion. And so in this sense, it is a solvent system model solvent. And the acid-base part comes in when you have a substance that can increase the concentration of the cation. That is going to be the acid. And for the base, it's going to increase the concentration of the anion. And so when we have ammonia as our solvent, we can have ammonium chloride as an acid because it's going to increase, upon dissociation, the ammonium concentration. Well, we can have, say, sodium azanide as a base in ammonia, because upon dissociation, it's going to increase the anion azanide concentration. Well, the solvent system model is definitely a step forward, a more generalized definition than the initial Arrhenius definition in terms of water. Nevertheless, it really places heavy emphasis on the idea, on the fact that there must be a solvent that is auto-ionizable. But we do observe acid-base behaviors in situations that does not involve a solvent or at least an auto-ionizable solvent. And so, physical chemists Johann Nicholas Bronsted from Denmark and Thomas Martin-Lowry from England independently derived the Bronsted-Lowry model. And so by this definition, in a chemical reaction, the molecule that yields or loses hydrogen ion is the acid, so it donates a hydrogen ion in common terms. And reciprocally, that which accepts this proton, this hydrogen ion, serves as the base. So here's an organic example. Let's say I have an acetate ion, right? So this lone pair can accept a hydrogen ion from sulfuric acid. Very indicative by the name, right? So the sulfuric acid donates this hydrogen ion and becomes hydrogen sulfate. Well, the acetate serves as the base since it accepts this hydrogen ion. And also one thing you see that directly follows from this definition is whenever you have an acid, you also have a base. Then also there's the conjugate acid conjugate base concept, because the original base, after accepting a hydrogen ion, can also lose that hydrogen ion to return to its original state, so it can also has a conjugate acid. Well, the acid, after donating its hydrogen ion, can also reaccept the hydrogen ion, so it serves as a base, conjugate base. And so every reaction in this sense is actually an acid-base reaction, which is it messes up a little the concept of neutralization, because although you have acid-base reacting always, you do not always have a neutralized sort of understanding. But this concept of acid-base as the donation of hydrogen ions is a very useful definition. So now, having talked about the various definitions, I want to actually move on to our analytical example. And it has to do with something called kinetics and equilibrium. So kinetics, just for review, is the model of reactions, is how the study of how reactions proceed, right? And equilibrium is a state in which every substance that is involved in the reaction, the formation rate of that substance is also equivalent to the rate of disappearance, the rate of consumption. So overall, no net change of all the substances is observed. So in this sense, it is determined by kinetics, because the forward rate has to equal to the backward rate. Yet, the equilibrium constant is also independent of different mechanisms. And what I mean is, I can illustrate by this example. So we all know hydrogen peroxide, right? It can dissociate into, not dissociate, it can react to form water molecules and oxygen molecules, but it proceeds at a very slow rate. But there are enzymes in our bodies, peroxisome is one of them, that kind of degrades hydrogen peroxide and sort of serves as a catalyst. Now it does increase the rate, you would think, it does increase the rate of forward reaction. So you may think that the equilibrium constant is going to be somehow altered, because it does depend on when the two rates have to be equal to each other. But nevertheless, when you increase the forward rate, it also inevitably increases the backward rate. And so that's the reason that the overall equilibrium state is independent of different mechanisms of the reaction. So here's our actual example. It is a pretty typical one, and I think many of you may have seen it before. So essentially, it is adding hydrofluoric acid to water. And normally, to kind of analyze this situation, we make a few very useful and simplifications. So if we assume that initially we have no hydrofluoric acid in water and we're just adding it pure to water, then we can assume that the hydrofluoric acid concentration after equilibrium is attained does not alter very much, because here I have the concentration, the equilibrium constant for acid dissociation of hydrofluoric acid, which is pretty small, which means that the final concentration, final amount of hydronium ion and fluoride ion is really small. Their formation is really small compared to the hydrofluoric acid concentration, so they won't form very much. And also what we assume is essentially we assume the second and the third reaction doesn't really proceed, and so it's only the first. Now these are very reasonable assumptions, and they do yield very satisfactory results. But nevertheless, to kind of have a comprehensive illustration of how do we analyze reactions, not only acid-base reaction, but just equilibrium reactions in general, I want to make none of these assumptions. And so what chemical reactions are, they are means in which the concentrations, the quantities of reactants and products may change, right? So if I know, and they're the only means in which the concentrations of reactions and products may change. And so if I know how many times each reaction occurred, I can know the final concentrations of the products, because I know that these reactions are going to be the only means in which the quantities of the reactants and products can alter. And so what you may call the stoichiometrical unit and what I call the principal unit is essentially how much each reaction has occurred, right? And by convention, we usually denote delta rho 1, for example, for this reaction, to be the change in concentration for the reactant. So if we're adding this hydrofluoric acid to water, then this delta rho 1 is going to be a negative quantity because it's going to decrease. So, as we said, if we assume all these, if we know how many times each reaction has proceeded, then we can express all the concentrations, all the quantities of reactants in terms of these delta rhos. Right, so for example, I'll do for hydrofluoric acid, right? So hydrofluoric acid can react according to the first reaction. So, and also since it corresponds to the consumption of the product, so we just plus delta rho 1 here. It also appears on the right side, the product side of the second reaction, so we minus delta rho 2. And similarly, you can follow for all these 4 reactants or products that's involved in this series of reactions. And in kinetics, we know there's something called equilibrium constants. What they are essentially is that they are certain ratios of concentrations, some combinations of the concentrations of products over reactants, and they must correspond to a single value, right, a constant value. And so, as we know that we can express all these concentrations in terms of rho 1, rho 2, delta rho 3, and we see we actually have 3 equations here, right? Because each of them can be expressed in terms of delta rho 1, delta rho 2, delta rho 3. We seem to have 3 mathematical equations with 3 variables, which may seem to be a promising way that we can, solve for how much each reaction has proceeded, and so to know the final concentrations of the reactants. Now, before you very eagerly plug in all those values, which I actually do right here, you may notice one thing. You may recall that in kinetics, or from equilibrium study in acids and bases, that there is this equality of the water dissociation equilibrium constant is equal to the product of Ka, the acid dissociation constant, and the equilibrium constant for base dissociation. And what that entails is actually, when you multiply Kn and Kb, you obtain Kw. And what that entails is Kw, our third equation right here, really isn't an independent equation. It is a combination. It is a product of our first and second equation. And so we arrive at this dilemma that we actually don't have 3 equations for 3 variables. Instead, we have, as I have in the red frame right here, 3 variables, but 2 equations. But there turns out to be something you can do mathematically. Let's say you define delta rho A to be delta rho 1 minus delta rho 2, delta rho B to be a sum of delta rho 1, delta rho 3. You can actually express the 2 equations in terms of delta rho A and delta rho B. So we simplify, reduce the 3 variables to 2 variables. And in this, the 2 equations become solvable. And by knowing these 2 constants, since I know this is going to represent the final hydronium concentration, I have a way to kind of know what the final concentrations of each substance is going to be. Now, this works out mathematically, but what is the chemistry implication? Why is this so? Now, Mr. Walker in his chemistry, organic chemistry videos and classes used to tell us to sometimes pause for a second and think about it before he provides the thought. So if you would like, I would encourage you to do the same. Okay, so if you think about what equilibrium constants are, they are some relations of the final concentrations of the products and substance and reactants, right? So more generally, they are a sort of condition on the final concentrations of substances involved in the reaction. And recall what our dilemma is. Our dilemma is essentially that by the first reaction, reacting for the acid reaction and the base reaction, that the sum total of these two reactions is actually identical to the water dissociation reaction. So in other words, these two reactions are two mechanisms in which we have the same pattern of consumption of the same product, of the same reactants, and the production of the same products. So there's no way for us to distinguish them. And if we're only given the final conditions, the final quantities of these things, we don't necessarily know, we can't necessarily distinguish from which mechanism it came from, right? And this makes sense for combination, that we cannot know if we are only given the final conditions, the final quantities of the substances, how they actually got there. So essentially it is, we know the end, but we know not the means. I understand that my analytical example might have been a little tedious, since I contrived to be both thorough and comprehensive. So for the rest part of the presentation, I'm just going to go back to the more theoretical storytelling part. So we talk about the Bronsted-Lowry model being a very useful acid-base model, and in fact, normally when we use the term acid and base, we mean it in terms of the Bronsted-Lowry sense. But the Bronsted-Lowry model really focuses on the presence of hydrogen ions, and there seem to be reactions that do not involve the donation and acceptation of hydrogen ions. And so the Lewis model, developed by the American chemist Gilbert Newton Lewis, states that formally, a Lewis acid is one which by itself or a constituent of it accepts a pair of electrons, and the Lewis base is one that donates one lone pair of its electrons. So one example of Lewis acid base reaction can be shown here, right? So I have ammonia reacting with boron trichloride, right? Boron trichloride has an incomplete octet, so it wants to kind of get an extra pair of electrons to attain that octet, and so it's going to form a bond with the lone pair on the nitrogen here. So in this sense, the boron trichloride accepts a pair of electrons and therefore serves as a Lewis acid, while ammonia donates a pair of electrons and therefore serve as a Lewis base. And so this is an example of Lewis acid and base reaction. Now, Lewis model, the Lewis definition encompass the Bronsted-Lowry definition, because, for example, when you think about a Bronsted-Lowry base, right, a Bronsted-Lowry base is a hydrogen acceptor, hydrogen ion acceptor, and in order for it to accept that hydrogen ion, it has to have a lone pair, right? So it has to be a donor of a lone pair, so therefore it's a Lewis base. And a Bronsted-Lowry acid, right, a Bronsted-Lowry acid donates a hydrogen ion. And for that hydrogen ion to be donated, it has to obtain a pair of electrons. There has to be a pair of electrons that's going to take that hydrogen ion, that the hydrogen ion can latch onto. And so that hydrogen ion part of the Bronsted-Lowry acid is going to serve as a part that accepts a pair of electrons. And therefore, a Bronsted-Lowry acid is also a Lewis acid. Now, if you kind of now look back upon our progression of understanding, our progression of definitions for acids and bases, we went from a very particular solvent, water, to a general solvent, to a general solvent. And then we went from there, kind of diverged a little bit to kind of focus on hydrogen ions, donation and acception of hydrogen ions. And then we came to this electronic understanding of acids and bases, electronic definition. So we have come from something very specific to actually something very, very general. Because electrons are really the things that are involved in all chemistry bonding, chemical bonding, that are involved in all chemical reactions. And indeed, there are even people who want to push the understanding a little bit further. They want to define an acid as any substance that's going to gain electron density, and a base is any substance that would donate electron density. So the Lewis definition of acids and bases, the electronic definition, is really a kind of general understanding of chemical reactions. And when we do generalize acids and base into this understanding of electronic reconfiguration, then what acid-base reactions are, what acid-base reactivity are, becomes the just general reactivity of reactions. And I like to end by using one of Gilbert Newton-Lewis' quotes. He says, "To restrict the group of acids and bases to those substances that contain hydrogen interferes as seriously with the systematic understanding of chemistry as would the restriction of the term oxidizing agent to substances containing oxygen." Thank you. I hope you find this presentation useful.